Hello everyone, my name is Miao coming from Nanjing University of Aeronautics and Astronautics. Today, I will introduce our recent work, Deep Multi-View Channelized Spatial-Temporal Network for Traffic Flow Prediction. We have following 4 parts: background, method, experiments, and conclusions. So, if you know something about spatial temporal data mining, especially in terms of transportation, you should learn that traffic prediction is very important. As a typical part of spatial temporal prediction tasks, traffic prediction has drawn considerable research attention in recent years due to the increasing amount of urban traffic and its significant impact on real-world applications. However, there are lots of traffic observations such as vehicle speed, road occupation, and traffic flow. Different types of traffic observations may have different impact on traffic flows. The left part of this figure shows the relationship between traffic flow and traffic speed. From the picture, we can see that traffic flow and speed are negatively correlated. That's to say, the traffic speed will slow down with the increase of traffic flows, and vice versa. The right part of the figure shows the relationship between traffic flow and road occupancy, while the change of road occupancy follows the change of traffic flows. Both traffic speed and road occupancy have impacts on traffic flows, but the two relationships are quite different. It's not considered in previous works how to model the influence of different traffic observations. So there are two challenges of existing works. The first one is that existing works mainly focus on capturing the local spatial correlations of the traffic data while ignoring the global correlations. The second one is about the traffic observations. Different types of traffic observations may have different impacts on traffic flows. Next, I will introduce two important notations in our work. The first one is traffic network G, and the second one is traffic network features matrix X. Given the notations, I will give you the problem definition. Given traffic network and the traffic network feature max and the external context data E, our goal is to predict the traffic data flow YT in the next time slot. In order to solve the above challenges, we propose our model MVC estimate. As shown in the figure, first, we split the raw input data into n parts, with each part indicating a channel. The local and global spatial temporal graphs are constructed from the geographical and semantic views, respectively. Next, several channel-wise layers are stacked to learn the hidden feature of each channel, which represents traffic flow, vehicle speed, or road occupancy. We assume that different channels may have different impacts on task prediction. The stacked CGCN layers aim to capture the spatial dependencies of the data and map the channel-wise data into a high-dimensional embedding latent space. Meanwhile, it also can adaptively learn the hidden relations between input channels and prediction. Third, after the multi-view fusion, the learned spatial features are imported into stacked LSTM layers to learn the temporal dependencies. Finally, we concatenate the learned spatial temporal representations and the learned external features for prediction. These formulas show the details of local and global spatial temporal graph construction and multi-view channel-wise graph convolutional network. And this picture shows the framework of channel-wise graph convolutional network. If you are interested, you can read our paper. Besides the spatial correlations, traffic flow forecasting also involves complex temporal correlations. We input the extracted spatial features into LSTM layers as follows for temporal feature learning. In our experiments, we use PMS04 and PMS08 dataset, and the description of these two datasets can be seen in the left figure. MA and RMSE are used as evaluation metrics in our experiments, and the loss curve of about two datasets can be seen in this figure. This table shows the performance comparison among different methods over the two datasets. It shows the proposed model MVCSTNet achieves the best performance among all the methods on both tasks. To study whether the components in MVCSTNet are all helpful to the prediction task, we compare with its variants that remove the channel-wise convolutional network, multi-view fusion, or global spatio-temporal graph. The result is shown in this table. One can see that CGCN and multi-view fusion model are all useful to the model, as removing any of them will increase the prediction error. To further intuitively illustrate how accurately our model can predict the crowd flows, we realize the predicted crowd flows and ground truth in one figure as depicted in this figure. One can see that the red curves of prediction can accurately trace the blue curves of the ground truth, including sudden changes, which demonstrates the effectiveness of the proposed model. In conclusion, we propose a novel deep multi-view channel-wise spatial-temporal network named MVCSTNet, and adopt a channel-wise graph convolutional network to learn the divergence between channels and consider localized and globalized spatial-temporal graph.